Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. Every day we're in environments where sound sources are separated from receivers by layers, walls, and partitions. In this video, we'll learn how sounds reflect and transmit through these interfacing layers.
So let's get started. Understanding how waves propagate through layers is critical when we design buildings, aircraft, vehicles, all sorts of consumer products, and much more. Every time a wave arrives at an interface, a portion of it is reflected and transmitted. And in order to determine the relative contributions of reflected and transmitted waves, we need to develop a simple theoretical model. Here, we introduce an interface layer with thickness L. It starts at the plane x is 0 and goes to the plane x is equal to L. Our incident and reflected pressures are exactly as they were before, but our transmitted acoustic pressure has wave number K3, since it has a specific acoustic impedance R3. The layer that is bounded by the incident and transmitted fields has incident acoustic pressure P sub A with complex amplitude capital A and then e to the j omega t minus K2x. The reflected acoustic pressure in the layer is lowercase p sub b is equal to capital complex B e to the j omega t plus K2x. We still have the same boundary conditions here that we had before: continuity of acoustic pressure and continuity of normal specific acoustic impedance. On the other hand, we have to apply continuity at both of the interfaces. And in fact, this result, in theory, ends up being highly complex to express. Once we simplify it, we can find the pressure reflection coefficient first. It is in general complex because we see the imaginary number j in both numerator and denominator. This doesn't mean that the reflected pressure is damped. It just means that the phase of the reflected wave may be different than the phase of the incident wave. The power transmission coefficient, on the other hand, is purely real, and it's at most a quantity of 2, which is the same as we found for a single fluid interface. A common example when we apply these coefficients is for an incident and transmitting fluid of air, in which case R1 is equal to R3. And now let's consider an example of this office space. We've got air on the inside of the office, air outside the office, and in between we've got a glass wall. We've got a bookcase. We've got a floor, and so on and so forth. In these cases, R2, the impedance of these layers, is much greater than R1. Also, they're very thin compared to the size of the air in the incident and transmitted fields. In this case, we can drastically simplify our power transmission coefficient, capital T sub capital pi. It's equal to 2 on K2L multiplied by R1 divided by R2 quantity squared. This is called the mass law. It shows us that transmitted power is inversely proportional to the squared mass per unit thickness of the layer. So in other words, if we double the layer mass by thickness or density change, we reduce transmitted power by 6 decibels, where the decibel quantity is determined by taking 10 log 10 of our power transmission coefficient. This result is accurate so long as the span-wise dimensions, for instance A and B here for the glass wall, are much greater than any given wavelength considered. Another common implementation of this theory is in the practice of impedance matching. One outlet is when we use ultrasonic transducers. The piezoceramics that make up many ultrasonic transducers have very high density and sound speed in comparison to the materials that we monitor, such as in construction materials, biomedical monitoring, manufacturing quality control. The density and modulus of these materials is much less than brittle piezoceramics, and this leads to poor signal-to-noise ratio because most of the power is reflected. Take, for instance, tissue. In biomedicine, tissue has density around 1,000 kilograms per meter cubed, just like water, and it passes sound at around 1,540 meters per second. If we directly apply that piezoceramic of the ultrasonic transducer to the tissue, almost all of the pressure and power would be reflected. Instead, we introduce impedance matching layers by designing the impedance to be the geometric mean of the adjacent layer impedances, and the thickness of the layers are determined according to integer number of wavelengths. In this case, the resulting transmitted acoustic pressure is much greater in amplitude with the impedance matching than without. We see that here in the simulation. The simulation at top does not have impedance matching layers. The piezoceramic is directly applied to the tissue. At bottom, several impedance matching layers gradually reduce the impedance from the piezoceramic quantities down to human tissue to enhance the acoustic power transfer. So let's summarize what we've learned. We found that waves transmit through layers according to the compatibility of the adjacent layer impedances. We've found that the mass law shows that a 2 times or 1/2 times of layer material, whether by changing thickness or density, results in a plus or minus 6 dB change of the power transmission. And impedance matching is one common implementation of this theory. It helps us design ultrasonic transducers and interfacing layers to best transmit acoustic power for things like structural health monitoring, biomedical ultrasound, quality control in manufacturing, and much more.
That's it for this video. And the next video will gather intuition regarding how waves reflect and transmit when arriving at oblique angles to interfaces.